Hi, today we're going to look at the 2019 AP Statistics exam. This is free response question number 3. It has to do with probability, independence, and the binomial distribution. So let's take a look at it and see what they tell us. A medical researcher surveyed a large group of men and women to ask them about whether they take their medicine as prescribed. And the answers they were able to give were things like they could say I never take my medicine, or I sometimes take it, or I always take it. Those kinds of things. And then over here on the right, on the left of the side of the triangle, that is, we have the gender. Okay, so I think a good thing to do when you look at these problems, you first look at them all. One good thing to do is take a look and see if you even understand what each data entry means. So here's what I mean. Let's say I circle this number 0.2016. What is that telling me? Well, if we're in that position, we're in the sometimes column. You can see that on the top. We're in the men row. So this is telling us that 0.2016, or about 20%, we'll say, 20% of the people in this survey were men who sometimes take their medication. So notice how I'm saying that. I'm saying that as men who sometimes take their medication. I'm not saying this is of the men that sometimes take their medication. This 0.2016 is out of the entire survey. All right. Similarly, if I were to look, say, at this number down here, this number is in the always column. It's in the woman row. So we can say 0.3280, or about 33% of the people in this survey were women who always took their medication. Okay, great. Let's start to answer some probability questions and see what they're telling us. So first question right here, little number 1 there. What is the probability that the person selected will be someone whose response is never and who is a woman? Response is never and is a woman. So we look in the woman row and we look for the never column, and that's right here. You can see it. Let me just erase the other stuff that I don't need anymore. Not interested in that. Okay, and so you can see is this is a position where we're in the woman column and the never column in the woman row. And so that's it. That's the answer to this little part A here, 0.0636. Not bad. Okay, next question says, what's the probability that someone will be selected whose response is never or who is a woman? Okay, so the word or in probability, sometimes you might think, well, the word or means add, and you're pretty much correct there, but you got to be a little bit careful. So there's a formula in probability that says the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So in our case, we wanted the probability that someone said never, I never take medication, or the person was a woman. So according to this definition above, we would get this result. We would get, so you'll notice everywhere there's an A, I'm putting an N, which stands for never, a person who never takes their medication. Wherever I see a B, I'm putting a W. So there it is, B is W, and I'm just replacing that everywhere. Okay, I sometimes like to look at this just to understand where this formula comes from. If you just take a look at a Venn diagram, it's sort of a nice thing that shows this. If we took the circle N, which represents all the people who say, I never take my medication. We took the circle W, which represents all the women in the study. There are definitely women who never take the medication. We can see that here. That was the answer to Roman numeral 1. So that number represents women who never take their medication. And so we can see them here in this part of the graph. So we wanted to, we could even put a 0.0636 here. Okay. So you can see if you were to just, for example, let's say someone said, I know that or always means addition in probability questions, and they just added the people who never take their medication, plus they added all the women in the study. They'd be making a mistake because they would be double counting the area, right, where there are women who never take their medication. So that's the problem with just adding these two probabilities up here, is that you'd be double counting the overlap. And so that's where the subtraction comes from. We subtract it out one time so that we don't double count it, we just count it once. All right, let's actually apply the formula by looking at those probabilities. So the first thing we're going to do is the probability that someone is, let's look at it, someone who never takes their medication. So that's this one right here. So if we look at the table here, probability someone never takes their medication is right here at the bottom, 0.12, 0.1200. Plus, the next thing we're going to need is the probability that someone is a woman. So if we look up here, probability someone's a woman, that's over here, 53% or 0.53 of the people in this study were women. And then we're going to subtract off probability of woman and never takes their medication, but we already know that number is 0.0636. So this is just a matter of carefully putting this into your calculator. Let me do that for you. 0.12 plus 0.53 minus 0.0636 gives us this number, 0.5864. So that's that. That's what that question's about. All right, so on to the third part of this question. Let's go to a new page here. I'm getting a little crowded with information. So the question we're working on is right here. What is the probability that the person selected will be someone whose response is never, given that the person is a woman? All right, so be really careful. When you see the words given that means you have something called a conditional probability. So we have notation for that. We can say the probability of A given B occurred. In our case, we want the probability. If we read it again, it says it right here. Let's not lose track of it. We're right there. It says the probability that someone whose response is never, given that the person is a woman. So we're using our notation. The response is never, given we're speaking with a woman. And it turns out there is a formula for this. It says you do the probability of A and B divided by the probability of B. I like to think of conditional probabilities as you're restricting your sample space. You're saying, I only want to consider a certain group of people and say, what's the probability out of that particular group? So in our case here, we're saying, what's the probability that someone's never, says I never take my medication as a woman, over just the probability of women? In other words, we're only going to ask women this question, and what's the probability now? So both of these numbers, the numerator and denominator, exist in the table. So the probability of, right here, it's never and women over probability of women. So never and women is right here, 0.0636, 0.0636. And then we got probability of someone being a woman in this study. That's 0.53. So it's going to be over 0.53. So we just got to divide these, see what happens here. 0.0636 divided by 0.53. And I'm getting exactly, not even an approximation, but exactly 0.12. So that's our probability. Okay. Something I would say to look for whenever you see the word conditional probability in a question, it's often followed with, is there independence between these two variables? So we look at the next question. It says, for the people surveyed, are the events being a person whose response is never and being a woman independent? Okay, so that's what we're asking now. Are these two variables independent? And it turns out that this conditional probability can help you answer that. So there's really two ways to test for independence. Here's one of them. First, you can check, does the probability of saying never equal the probability that you say never given that the person was a woman? The second way to check it is take the probability of I say never and I'm a woman and see if that equals the product of someone who says never times the probability that someone is a woman. So these are your two options for checking for independence. You don't have to do both of them. You can do either. I will say that I think the second one's very easy to do. Probability of saying never and being a woman, according to the table, is 0.0636. The probability someone says, I never take my medication, is right here at the bottom. You can see me circling it, 0.12. And the probability someone's a woman in this study, you may remember it, but just in case, it's over here circled in blue, 0.53. So we'll put that 0.53 here. So you just got to see if these two things are equal. If they're equal, then they're independent. So if I multiply them for you, 0.12 times 0.53, turns out that this side of it, this side of the expression equals exactly 0.0636, which matches the other side. So yes, we can say that being a woman and saying I never take my medication are independent events. So gender does not affect the likelihood of someone saying I never take my medication, at least in this problem. Okay, let's look at the other way to check it. Now, I will tell you in my early statistical days, I liked this method here on the bottom better because I just thought it was easy to do. Just plug everything in and see if it works. Now that I've been doing statistics for a while, I like the top one better because I think it makes more intuitive sense. Okay, so the probability that someone never takes their medication is in the table. So if we look at the table here, never takes the medication, there it is, 0.12. So I'm going to put a 0.12 here. The probability that someone never takes the medication given they're a woman, that was actually the answer to the question right above it, right? Question number 3, that conditional probability. And we calculated that, and it turned out to be 0.12. So these things are the same. So that tells us, yes, that these two variables are independent. But with this first formula, I like to think about why it tells us it's independent. It tells us it's independent because the probability that any old person, male or female in this study, says I never take my medication is 12% or 0.12. If we just ask women, if we say what's the probability someone says they never take their medication given they're a woman, the probability doesn't change. The probability wasn't affected by the fact I knew I was asking a woman the question. So in this case, what we're finding out is that between men and women, there's no difference. That variable, men or women, does not have an effect on the likelihood of them saying, I never take my medication. So intuitively, I kind of like the first one better. Okay, one more question to go here. If we look at the last part, C, we read that question there. Let's extend the page a little bit. Let's see what this says. So we're looking right here. It says, assume that in a large population, the probability a person will always take their medication, P, is 0.54. If 5 people are selected at random, so that's sort of like a sample size of 5, what is the probability that at least 4 of them, okay, will say they take their medicine as prescribed? Okay, so notice you have a fixed number of people that you're speaking with, and you're counting up. You're interested in the probability that at least 4 of them say, yes, I always take my medication. You should recognize this as a binomial setting. Why is it binomial? Because we have a fixed number of trials, 5 trials, and X equals the number of people who always take meds. So X is a count of the number of successes amongst 5 people. That's how you know you have a binomial setting. All right, so how do we do it? So there's really 2 ways to do it. The probability that X is greater than or equal to 4, we could think of this way. Well, if 4 people out of 5 said they took their medication, that would be considered something we want to know about. That's a success. And also, if 5 people out of the 5 said, I take my medication. So there we are. We just want to compute these 2 probabilities. You have some options. One thing you can do is you can use something called Binomial Pdf in a TI-84 calculator. That will always ask for, if you go to, just to practice it, you always type in the sample size first, the probability of success on each trial, and the number of successes you want to see. That's how it works. If you want to see where it is in the calculator, you do second vars, the distributions is where you're going. Go down or up until you get to Binomial Pdf. It's next to the letter A. Trials are going to be 5. P is going to be 0.54. The X value is going to be 4. Hit paste and enter, and you get 0.1955. That would take care of this probability. You have to do it again. Binomial Pdf 5, 0.45, 5. If we do that, we get an answer of 0.0459. And we just want to add these two things together because either the first thing happens, we get 4 out of 5 people say, yes, I always take my medications, or the second thing happens, all 5 out of 5 say they take it. 0.1955, we just want to add these numbers, so let me do that for you. See what we get. Hold on a second. And we are getting around 0.24, 24% of the time this would occur. Okay, finally, you should know that there is a formula for a binomial probability. So if you were going to use a formula, you might see this in textbooks or someplace else. The probability x equals exactly k is n choose k, p to the k, 1 minus p to the n minus k. So it certainly looks scary, but it's actually not that bad. So in our first case, we wanted the probability that x equaled 4. I'll just calculate that one to show you. You put a 5 here, a 4 here. P is 0.54 for this problem. Don't forget that k is on the bottom here, and it becomes your exponent. So your exponent here is going to be 4. 1 minus 0.54 is 0.46, and your exponent is going to be, in this case, 5 minus 1. I'm sorry, 5 minus 4, which is 1. Okay, good. So we just need to calculate this. Most calculators, the T84 in particular, which most people use for this class, does not have anything that looks like that, but it does have something that looks like NCR, which is what you really want to use. You want to do 5, choose 4. If you need to find that, there's a button on the left-hand side of the calculator, the third button down that says Math. You press Math. You hit your right arrow, you go over 4 times, you land on the probability menu, PROB, and you go down to number 3, it says NCR, and you can put the 5 and the 4 that you want in the right locations, and when you're done, you'll get just 5 as an answer. So next, you just do 5 times 0.54 to the 4th times 0.46 to the 1. And if you type that in, amazingly, you'll get 0.1955, which was exactly the answer we got when we did that binomial PDF function. So I would expect most people to just use that binomial PDF function, but just in case you wanted to know where it came from, that's it right there. Okay, great. That problem's done. Thanks for watching.